Hello dear students. In this video we will solve a couple of problems related to Newton's law. The problems that we will do in this session are from the textbook University Physics with Modern Physics by Hugh D. Young. Before we begin, let us quickly recap the Newton's first law. So this entire session we will be doing problems from the Newton's first law itself. And the Newton's first law says that if the net force acting on a body is zero, then the object or the body is in equilibrium. Or at the same hand, we can also state this law like this, that if a body is in equilibrium, which means either it has zero velocity or if it has a constant velocity, then that implies that the net force acting on the body should be zero. Even though this equation looks like a single equation, this can be split into three different equations within the component form. This implies that the sum of all the x components of forces should sum to zero so that the body is in x directional equilibrium. Sum of all the y components of forces should be zero. Then only the body will be in equilibrium along the y direction. And similarly, you can write an equation for the z direction as well. For two-dimensional problems, we will usually use these two equations in order to find relevant quantities. Now, solving problems using Newton's law, it mainly consists of three parts. The first part is setting up the problem. In this part, we try to draw a simple sketch of the given setup. Then from that, we will try to draw the free body diagrams. If there are more than one body involved in the problem, there will be that many number of free body diagrams. Then within this free body diagram, we will be identifying the forces that are acting on the body and correctly mapping them. When you draw that, you should pay attention to the fact that only the forces acting on the body should be marked on the free body diagram of a particular body, not the force that the body applies on something else that should not be mapped on the free body diagram of a particular body. Then you should choose a particular coordinate axis to solve the problem. Usually we do the horizontal side as the x direction and the upward side as the y direction. Sometimes in tilted kind of problems, when a body is climbing up a scale, we can also choose this direction as the x direction and the upward direction as the y direction. So this is the first part, which is the setting up of the problem. In the second part, we execute the solution. So from the setup part itself, we have identified the components of each forces along the different coordinate axes, and then we apply the Newton's law. For example, if we understand that this is a context where Newton's first law applies, we will apply the Newton's first law. So how do you identify whether Newton's first law or second law applies to a body? Check whether the body is in equilibrium or not. Check whether the body is accelerating or not. If the body is not accelerating, that implies that this is the context for Newton's first law. That means that sum of all the forces acting on the body is zero. Sum of all the x components of forces acting on the body should be zero. Sum of all the y components of forces acting on the body should be zero. The third part involves evaluating your answer. And this is the easiest part. Here you just have to analyze whether the dimensions or the units that you have obtained matches with the theories. And you can also check for extreme values or special cases and check if your answer makes any sense in those cases and check whether you have got a reasonable answer. For example, if you are applying force along the x direction, then you should have an understanding that it will result in an acceleration along the x direction itself. So if you are getting a negative acceleration, that implies that your answer itself is wrong. So similarly, by applying logic, the logic of dimension, extreme values and reasonableness, you can understand whether the answer you have obtained is correct or not. Now let us apply what we have learned into certain problems of Newton's first law. So let us first consider a case of two-dimensional equilibrium. This is example 5.3 from our reference book. In the figure, a car engine with weight W hangs from a chain that is linked at ring O to two other chains, one fastened to the ceiling and the other to the wall. So that is given in this picture. A weight W, a car engine with weight W is hanging on a chain which is attached to a ring, and the ring is supported by two other chains, and on each of this chain it is having a tension given by T1, T2 and T3. Find expressions for the tension in each of the three chains in terms of W. The weight of the ring and the chains are negligible compared to the weight of the engine. So this is the illustration of the problem. Even if the illustration is not given, you can get an understanding from this question itself. So this third chain, it is at an angle of 60 degree with respect to the ceiling. So now you already have the setup of the problem. Now you move on to the first part where you have to draw the free body diagram of the problem. Can you try drawing the free body diagram? So here we have given the free body diagrams. You have to draw two free body diagrams. One is enough to solve the problem. But here are two bodies. One is the ring and the other one is the car engine. In the case of car engine, it is remaining stationary, so it is in equilibrium. So there are two forces acting on this car engine. One is the weight of that car engine acting downwards, which is given by W, and an equal and opposite tension force that is applied by this chain T1. It is acting upward. The engine is in equilibrium because sum of all the forces acting along the y direction on this engine sums to 0. That means T1 plus minus W, that is equal to 0, which implies that the T1 is W itself. So from the free body diagram of the engine alone, you can understand that the tension on the chain 1 should be equal to the weight of the engine. Now let us draw the free body diagram of the ring. Can you try drawing that and check whether your answer is correct or not when I explain? So on the ring, there are three forces acting, T1, T2 and T3. T1 is the tension that is acting downwards. In the case of engine, the tension holds it up, and in the case of the ring, the tension on the rope is pulling it down. And from the left, the tension acting from the left side chain pulls it towards the left, and the tension applied by the chain on the ceiling pulls it at a particular angle. So in the problem, it is given that this angle is 60 degree. So from understanding that these two are parallel lines and this line cuts that, you should get that this angle should also be 60 degree. So I can simply write this angle is 60 degree. Now can you try to split this particular T3 into components? For that you should choose some coordinate axis. Here the simplest axes are this horizontal axis to be x-axis and the vertical axis choosing it to be the y-axis. You can see that T1 already lies along the y-axis, T2 lies along the x direction, only T3 has a random direction with respect to x and y axis. So you have to split this T3 into x and y components. Then only you will be able to put it into the Newton's first law equation and solve. Can you try to split this T3 into components? The components of T3 are like this. So this T3, if this angle is 60 degree, then the adjacent side, you can take it as T3 cos 60 degree, and the opposite side, it will read as T3 sin 60 degree. So now you have splitted all the forces into x directional forces and y directional forces. Now you know that the ring is stationary, so it's in equilibrium. So the sum of all the forces along the x direction should sum to 0, and similarly for y direction. What are the forces that are acting along the x direction? It is T3 cos 60 degree along the x direction and T2 along the minus x direction. So the sum of the forces reads as T3 cos 60 plus minus T2. Minus some sign comes because T2 acts along the negative of x direction. So that should sum to 0. Why? Because the ring is in equilibrium. Now the sum of all the y components of forces should sum to 0. That means T3 sine 60 degree, which is acting along the plus y direction, plus minus of T1, which is acting along the minus y direction, that should sum to 0. So from these two equations, you can get certain terms that relates T3 with T1. T1 you have already found out to be W. Now can you write T2 and T3 also in terms of W by solving these equations? Pause this video and try to write T2 and T3 in terms of W. So from the first equation you can get T3 sine 60 degree equal to T1 or T3 equal to T1 divided by sine 60 degree. Since T1 is already found to be W, it's W divided by sine 60 degree, and you can use your calculator to find 1 by sine 60, and you will find that T3 is equal to 1.2 times the weight of the engine. Now you will have to use this knowledge back into the second equation to find that T2 equal to T3 cos 60 degree, and here for T3 you can substitute 1.2 W. From that you will get T2 to be 0.58 W. So now you have got all these three tensions in terms of W. T1 is W itself, T3 and T2 are given by these two equations. So the problem is solved. When an engine is connected by three different chains, each of them having T1, T2 and T3 tensions as shown in this figure, then if the weight of the engine is W, then we can find T1 to be W itself, T2 to be 1.2 times W, T3 to be 1.2 times W and T2 to be 0.58 W. So which of these chains should be stronger, or which one is more prone to a breakage if the weight is high? Can you guess which one will break faster if the weight of this engine is above certain limit? So the key concept that we get from this problem is that in two-dimensional problem that involve forces, always write two equations for each of the object, one for x components of forces and one for the y components of forces. And by suitably using these two equations, you would be able to find out relevant quantities, what's the equilibrium state, and so on. Now let us do another problem from the Newton's first law itself. It's an inclined plane related problem. Consider a car of weight W resting on a slanted ramp attached to a trailer as shown in this figure. Only a cable running from the trailer to the car prevents the car from rolling off the ramp. So this chain is actually supporting this entire car, and this angle between the ground and the slanting rail is alpha. The car's brakes are off and its transmission is in neutral. Find the tension in the cable and the force that the ramp exerts on the car's tires. So from this setup itself, we know that the body is in equilibrium. The car and the trailer together may be moving at a constant velocity. And with respect to the frame of reference of this pulling vehicle, the car is remaining stationary as well. So first, identify the setup, form a brief sketch of this problem, and the next step is to draw the free body diagram. So can you draw the free body diagram of this car given all these forces acting on it? It's already given in this picture. So this is the setup, and from that you can draw the free body diagram. A single point can represent the body, and there are three forces acting on it. One is the tension applied by the chain, which is in this particular direction. The normal force always acts perpendicular to the surface. So since this ramp is inclined, the normal force will act perpendicular to that inclined plane. Weight of the body always act downwards. So this is the direction, W direction of weight. Now choose a coordinate axis. You can choose any axis to solve this problem. You can either choose the horizontal axis to be X and the upward direction to be Y. But in this context, since two of the forces already lying in one particular direction, for example, the tension is in this direction and the normal force is in the normal slanting direction, if you rightly choose the x-axis to be the direction of the ramp, that is, if this is the x-axis and if this direction is the y-axis, then two of your forces will already be lying along that direction. You will only have to split W into x and y components then. So identifying that, it's better to choose the direction of this inclined plane to be x direction and its perpendicular direction to be y direction. Now let us split the weight into components so that you have all the forces in x and y directions only. Can you try splitting this weight into its components? So from the idea that we have already learned, the W that is lying downwards can be split into vertical component and horizontal component. Now this vertical component, it is at the adjacent side, it is related to the alpha like W cos alpha. So can you show that if this angle is alpha, this angle is alpha as well? Can you show that? We can show that this angle is alpha by using certain laws from the geometry. So if I draw one more line here along the direction of our chosen y-axis, you can see a triangle over here, right? So this triangle, if this angle is alpha, since this is 90 degree, this is 90 degree, you can prove that this angle is actually 90 minus alpha. Since sum of all the angles of the triangle should add to 0, if this is 90 degree and this one is alpha, this angle is 90 minus alpha. So given that is 90 minus alpha, if I choose another triangle here, which is given by this triangle, this violet purple color triangle, so its one angle is 90 degrees, a right angle triangle, and the other angle is 90 minus alpha. Can you predict what this angle will be? This angle will be alpha. So if you know this angle to be alpha, then from the laws of triangles, from the how the angles are arranged in triangles, you can see that this angle will also become alpha. So that is how this angle is written to be alpha. It's not directly coming from this picture. You will have to predict that. You will have to find that this angle is also alpha. Now given this angle is alpha, the weight can be split into adjacent side, which is W cos alpha, and the other side, opposite side, which is given by W sin alpha. Now what are the forces that are acting along the x direction? This is your x direction. So along that direction, you have tension and W sin alpha on the opposite direction. And along the y direction, you have normal force acting upward and W cos alpha acting downwards. Now, can you write the Newton's law and solve them in order to find this tension force? So along the x direction, you can sum the forces to be T plus minus W sin alpha to be 0. The car is in equilibrium. Minus sign comes because the W sin alpha acts along the negative x direction. Along the y direction, normal force plus minus W cos alpha sums to 0. Minus sign comes because this acts along the negative y direction. So solving that equation, we will get that T to be equal to W sin alpha, which is asked in the question, and N equal to W cos alpha. So depending on this alpha, the tension and the normal weight that is experienced by this car will change. So now let us evaluate the answer. In this third part, let us see if this answer makes any sense. So what will happen if you increase the alpha? You are tilting this inclined plane even higher. You will have a higher angle here. So what will happen to the tension force then? It should increase, right? Sin alpha will increase with alpha and tension will increase. That we will experience, that we have experiences in our real life also. If the inclined plane is slanted at a higher angle, you will have to apply a higher tension force and the body will have lesser amount of normal force. Suppose you incline it and make it equal to 90 degree. This is an example of an extreme case or a special case that we mentioned at the beginning when we explain how to solve the problem. So if alpha equal to 90 degree, we know sine alpha is equal to 1 and then the entire tension becomes equal to W. That means if alpha equal to 90 degree, you are suspending this car just downwards. The entire weight is now acting downwards and the tension has to support the entire weight. So you are getting the exact same answer. So your answer makes logical sense. T equal to W sine alpha makes logical sense. Similarly, N equal to W cos alpha, you can think and understand that as you increase alpha, the normal weight decreases. And when you make this lie perpendicular, there is no normal force, which is the same that we experience in our real life as well. So this is how you evaluate whether your answer is correct or not. The key understanding that we get from this problem is that in two-dimensional equilibrium problems, choose the coordinate axis so that as many forces as possible lie along either the x or y axis. So in this previous problem, you could have also chosen the horizontal line to be x-axis and the vertical line to be y-axis. In that case, the normal force and the tension force, you would have to split it into components in order to solve the problem. But by rightfully choosing the x and y axis to be along a different direction, you only had to split W to be along x and y axis directions. So that is how you rightfully choose the coordinate axis in solving Newton's first law. Now let us do another problem from the Newton's first law itself. This is example 5.5 of our reference book, which is the equilibrium of objects connected by cable and pulley. So let us read the question. Your firm needs to haul granite blocks up a 15-degree slope out of a quarry and to lower dirt into a quarry to fill the holes. You design a system in which a granite block on a cart with steel wheels, weight W1 including both block and cart, is pulled uphill on steel rails by a dirt-filled bucket, weight W2 including both dirt and bucket, that descends vertically into the quarry. How must the weights W1 and W2 be related in order for the system to move with constant speed? Ignore friction in the pulley and the wheels and ignore the weight of the cable. So can you imagine this setup? So this is shown here in this picture. You have a cart which consists of some granite block and also a bucket which consists of some dirt. At the same time, you have to descend this bucket down to the ground and ascend this cart up a hill which has an angle of 15 degree. So you build this setup and now the bucket is slowly moving downwards at constant velocity without accelerating, and when the bucket moves downwards, the cart slowly climbs this hill at constant velocity. So since both of them are moving at constant velocity, this is an example of Newton's first law. So can you try to draw the free body diagrams in this scenario? So this is a simple illustration of the problem. You can see the weights are marked correctly, angle is drawn, the cart is shown as a block and the bucket is shown as another block. So there are two bodies involved, so you will have to draw two free body diagrams. So first let us draw the free body diagram of the bucket. The bucket is moving downwards. It is acted upon by two forces. One is its own weight, which is given by W2 acting downwards, and the tension on this chain, which is acting upwards, which is given by T. The tension on this chain is uniform since it's not accelerating. So on one side, on one end, the tension is holding this bucket upwards with T. So the same tension acts on this cart as well. So when you draw the free body diagram of the cart, what are the forces that acts on it? Its own weight will act downwards, which is given by W1. Since it is placed on a hill On a small slanting surface, there is an additional normal force, N, which is acting perpendicular to the surface. And there is also the same tension force that is pulling this cart upwards. So there are three forces that are acting on this cart. The tension acting along this slanted direction, the normal force acting perpendicular to that slant, that hill, and the weight that always acts downwards. So what should be the ideal choice of coordinate axis in the case of this cart? In the case of bucket, the ideal choice is choosing the upward direction as y direction. And in the case of cart, you can choose this slanted direction to be the x direction and the other perpendicular direction to be the y direction. So even though this involves two bodies, for each of the body you can construct a different coordinates axis. You can exclusively construct a coordinate axis to solve for one particular body itself. So solving for the first bucket, what are the forces acting on it? Since the bucket is in equilibrium, the sum of these forces should add to zero. So can you write the Newton's first law equation and solve for T? So applying the Newton's first law in the case of the bucket, which is going downwards, there are only y components of forces acting, tension along the upward direction and the W2 weight acting along the downward direction. So you should put a negative sign. You get T plus minus W2 equal to 0 or T equal to W2. Now let us solve for the cart system. In the case of cart, the cart along the x direction, it is feeling a tension which is pulling it up the hill, and there is also a component of force that is acting along the negative x direction. You can find that component to be W1 sine 15 degree. 15 degree you will obtain just the way we got if this angle to be alpha. We had found that this angle also to be alpha, right? So in that way, you will understand that the x component of force is W1 sine 15 degree. So that should sum to 0. Or you can get that T is also W1 sine 15 degree. From the case of bucket, you got that T equal to W2. And from the case of cart, you obtain that T equal to W1 sine 15 degree. And since both tension acts on the same rope, and since the rope is also in equilibrium, these tensions are equal. That means W2 equal to W1 sine 15 degree. Sine 15 degree into W1. Or from this, you can get a relation between W2 and W1. So that means that if and only if the cart and the bucket share this ratio of weights, you will be able to design such a system where this cart and bucket moves at a constant velocity. If any of these weights changes so that this ratio is not satisfied, then the system will accelerate, fall down. Now, what's the key concept that you understand from this? If there is more than one object in a problem involving forces, you are free to choose different x and y axes for each object to make it easier to find force components. For example, in that specific case, the cart had one particular set of x and y axes, and the bucket you had another set of y and x axes. So you have the freedom to choose different choices of coordinate axes for different bodies even within the same problem. Now these are some of the homework problems for you. Can you try to solve this by your own on your notebook? Two 25 Newton weights are suspended at opposite ends of a rope that passes over a light frictionless pulley. The pulley is attached to a chain from the ceiling. What is the tension on the rope and what is the tension in the chain? So try to solve this problem, illustrate the problem, draw the free body diagrams, and from that write the Newton's equations and solve these equations to obtain what is being asked in the question. Now one more problem for you as a homework problem. Forces F1 and F2 act at a point. The magnitude of F1 is 9 Newton. Its direction is 60 degree above the x-axis in the second quadrant. The magnitude of F2 is 6 Newton. and its direction is 53.1 degree below the x-axis in the third quadrant. What are the x and y components of the resultant force? What is the magnitude of the resultant force? So this is not a Newton's first law problem. This is actually simply to find different components of forces and to add them. So can you solve these two problems on your notebook and find the answers? So that's all for the day. I hope you have understood a bit more about solving problems, especially from the topic Newton's first law. Try to work out additional problems that are available in the end of the chapter. Try to go through the textbook and read it and understand more about solving Newton's first law. There is a bit more explanation regarding the evaluation part, the setting up of the problem, execution, and so on. You can try to read and understand by yourself. Hope you were able to understand a bit more related to solving Newton's law problems. Thank you.